Today is day 6 of Unit 8. We started with this warm-up today, so you should pause the video, try the warm-up, and then play to check your answers. Okay, so first, just making sure you have the formulas, you remember the formulas. So first, the arithmetic. We have recursive and explicit. Next, geometric. Again, we have recursive and explicit. And then we have the finite arithmetic sum formula. So that's Gauss with his folding of the paper. So S sub n equals n over 2 times a sub 1 plus a sub n. And lastly, let's see, I guess I'll put this last one here on the end. So we have the finite geometric is S sub n equals a sub 1 times 1 minus r to the nth power over 1 minus r. Okay, number 2, you're supposed to find the sum. Hopefully you realize this is geometric and the r value is 1/2. So to find the sum, I know that I'm using that last formula that I wrote up there. So S sub, now I don't know the number of terms, so I can't fill that in yet. I do know 30 is the first term. And when I do 1 minus r is 1/2. And I'm going to do that to whatever power once I figure out how many terms there are over 1 minus 1/2. So I can actually simplify the denominator while 1 minus 1/2 is 1/2. Okay, so now I need to figure out how many terms there are, and we've done several now where we know the last term value, but we don't know the number of that term. So we take that value and we set it equal to the explicit formula and we solve for n. In this case, we said it's geometric, so we'll set it equal to the geometric explicit formula, which is right here. So we're going to take 15 over 4096, and we're going to set it equal to the first term, 30. Times half raised to the n minus 1. So I'm going to first divide by 30. So 15 over 4096 divided by 30, whatever that is, equals half to the n minus 1 power. So then I'm going to, let's see, did I simplify that? Looks like I did, yes. So 15 over 4096 divided by 30 gives me 15 over 12,880, which I think that might simplify, but I'll just leave it. It doesn't really matter. Equals half to the n minus 1 power. So I'm trying to solve an exponential for a variable exponent. I know that I need to take the log of both sides. So then when I take the log of both sides, I'm getting the quantity n minus 1 times the log of 1/2 equals the log of 15 over 12,880. So I'm going to divide both sides by the log of 1/2. So I'm getting n minus 1 equals the log of 15 over 12,880. Divided by the log of 1/2. And then I'm going to add 1. And when I do that, I'm getting n. I'll just put it over here, I guess. And I'm getting that n is 14. So now I know that 15 over 4096 is the 14th term, which tells me, because it's the last term, that there are 14 terms in that series. So I want S sub 14, and I'm going to take 1/2 to the 14th power. Now, when I do that, 1/2 to the 14th power and subtract it from 1, I'm getting 1. I think it actually comes out like 0.9999, so you're going to round that to 1. So this is 30 times 1, which is 30. So we have 30 over 1/2. And by the way, I probably should use the approximate since we did do a little bit of rounding there. But then I have 30 divided by 1/2, which means 30 times 2, which is approximately 60. So our sum is 60, approximately. Next, put it in sigma notation. So just write my sigma, write n equals 1. The upper index, when the lower index is 1, the upper index is the number of terms, so that's 14. And then remember, we just used the explicit formula, and this is geometric, so explicit geometric. Well, we already used the explicit geometric. It was right here, 30 times 1/2 to the n minus 1. So that's what I'm going to write. And that's it. That's my sigma notation. Okay. All right, so go ahead and put this one in your notes. So should look familiar. It looks almost exactly like what we just did. The only difference is I see plus dot 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 on the end and no ending term. So that means this is geometric and infinite. Okay, so we need to talk about how to simplify that. So I did kind of a demonstration in class using the classroom, but I'll try and recreate that here. So basically what I did was I just said that one wall of the room, so I'll just make this a wall, we called that 0. And then another wall, we called that 30. And we just said this was like 30 feet across. So like the width of the room was 30 feet. So if we were at 0, and 30. So when we start the problem, the series, we're at 30. Okay, so I just had somebody stand right there, okay, at 30. Now, then I had them move to 15 feet. So they went to the center of the room and stood. Then I told them to go to 15 halves, which is 7.5. So they moved to there. And you get the idea. Then 1/2 more of that. So 15/4. They went and stood, oops, right there. So then 15/8 came next and they stood right there. And then they just kept moving 1/2 of the previous number closer towards 0. Okay, now what happened in the classroom is actually what's happening here as well. When I'm trying to put my mark for halfway, I'm starting to have difficulties because it's blending in with the line that was the edge, that was the wall, that's 0, representing 0. So same thing happened in class. The person just kept getting closer and closer and closer towards 0, but they did recognize, students recognized that that person, technically, mathematically speaking, would never touch 0. Okay, now eventually they did touch the wall, but mathematically speaking, they wouldn't. Why? Because every single time we're multiplying by 1/2 of the previous number. Well, the previous number wasn't 0, and we're not multiplying by 0. So you and I both know that you can't get a product of 0 if neither of the two numbers that you were multiplying was 0. So that means as we're multiplying by 1/2 each time, we're getting closer and closer and closer to 0, but we're never actually going to reach 0. The output's never going to be 0. So that's how we visually represented this series. Now, if I were to graph that scenario, I'd be looking at just the first quadrant. If I start plotting these points, so 1 is my first term, 130, I'll just put it there. Then 2 is at 15, so all the way down here. And then 3 is at 7.5 here. And then 4 is 15/4 there. You get the idea. As we continue further on, getting larger x values, meaning further terms in the series, it's the y values are getting closer and closer and closer to 0, which means, graphically speaking, we have a horizontal asymptote at y equals 0. Okay, so what does that mean in terms of this series? In other words, the sum. This was us graphing the sequence, the 30, the 15, the 15 halves, the 15/4. But if we look at the sum of that series. So the 30 plus the 15, so the 30 here, this point, plus the 15, plus the 15 halves, plus the 15 fourths, and I keep adding those. That's what we're trying to figure out here. That's what the question says, find the sum. And hopefully you're realizing that as we get further and further down the line, remember, the x values are continuing forever, for infinity, meaning the term numbers, I'm going to keep going forever. But as we keep going, the y values are getting so close to 0 that eventually, pretty far down the line, we're just going to round and call that 0. Even though we are still adding on, the value that we're adding on is so insignificant that we're just saying that nothing's getting added on. So if nothing's getting added on, then once you go far enough down in the series with the terms, you're eventually going to get to adding 0. So that adding 0 is not affecting the sum any longer. So that sum would just be the first however many terms until what we're adding on is insignificant. So that's why, even though this is an infinite series and the terms will go on forever, that's why in some cases we are able to approximate the sum. And that's what we're going to do here. So when you have a geometric infinite series, the first thing you're going to do is you're going to check the R value. Specifically, we'll want the absolute value of the R value. So we're going to find the absolute value of R, and if the absolute value of R is less than 1, then the series, we say this when it's getting really, really, really close to an asymptote, we say that that converges. That's the mathematical term, converges. And if it's converging, it's, like I said, getting really, really close to the asymptote, which means it converges towards a sum. It's getting really close to a sum that we can approximate. So it converges to a sum of, and now I'm going to give you the formula that you would use. So the formula is S equals A sub 1 over 1 minus R. That's the formula that you're going to use. So when do you use that formula? You use it if it's geometric and infinite, and you've checked the absolute value of R and it's less than 1. Well, let's go to our problem now. So our R value is a half. So the absolute value of a half is a half, and a half is less than 1. So because the absolute value of the R value is less than 1, our series does converge, and we saw that with our graph here. And it converges to the sum. So I'm going to find the sum now. S is equal to A sub 1 is the first term, 30. And we're going to divide that by 1 minus R, which is 1 minus 1/2. So we have 30 divided by 1/2. Well, that looks familiar. We did that earlier. That's 30 times 2, which is 60. So the sum is, and again, we are approximating that, but the sum is about 60. For this entire infinite geometric series. Well, that answer looks familiar because if you recall in the warm-up, we found the sum of just 14 terms, right? We stopped. It was not infinite, it was finite, and that was 60. Now, keep in mind, the reason that came to be 60 was back here, 1/2 to the 14th power was so insignificant that it got rounded to 0. Which made this 30 times 1. And you'll notice the formula for a finite geometric is similar to the formula for an infinite. It's just that with the geometric finite, we don't have this 1 minus R to the n. Okay, so I get rid of that 1 minus R to the n, take that away, I do have my infinite formula, A sub 1 over 1 minus R. So that's why sometimes your infinite geometric series will have the same sum as a finite geometric series. If you were asked to find the sum so far down the line that the number that's being added on is no longer significant, it's just like you're adding 0, then you're going to get the same sum as if you were finding the entire infinite geometric series. Okay, so sum of 60 approximately. So now we're going to look at B, because we talked about when the absolute value of R is less than 1, but we didn't look at when it's bigger than 1. So here we have 15 fourths, 15 halves, 15 30. So you're seeing that R is 2. Okay. And in terms of our demo, so again, here's 0 and here's 30. So if I am starting at 15 fourths, I'm starting about here, right? And then 15 halves here, and then 15 halfway, and then 30, I'm right there. So what's happening? The numbers are doubling. Well, if I kept going even further, my next would be 60, right, which is all the way down here. And then my next would be 120 all the way down here. And what you're seeing is these numbers are just getting bigger and bigger and bigger. Well, if they're getting bigger and bigger and bigger, then it's not like the last one where we're like leveling, the graph's leveling off and getting close to an asymptote. That's not happening. And again, if I graph that, let me just do my first quadrant, my graph's going to be actually an increasing exponential. Okay, so it does have an asymptote, but that asymptote doesn't affect things here because our values just keep getting bigger and bigger and bigger and bigger. So the 60 turns to 120, turns to 240, and so forth. The numbers are getting bigger. So what happens is if the numbers are getting bigger, there's no way for me to approximate the sum. So in this case, it's geometric, it's infinite. We check the R value, which is 2. And 2 is bigger than 1. So here's what we say. If the absolute value of R is greater than 1, then the series diverges. Diverges means the numbers just keep getting bigger and bigger and bigger, or smaller and smaller and smaller, but they're not leveling off like we had here. No leveling off is happening. The numbers are just increasingly getting bigger or increasingly getting smaller. So if that happens, the series diverges and no sum exists. So when you're doing problems like this one, what I would want to see for work is that you discovered it was geometric and infinite, you checked the R value compared to 1, you saw that it was greater than 1, and that you then wrote the series diverges and no sum exists. That's what I want you to write. Okay, so let's try this one. So this time, you want to copy that. This time we have what we can tell, hopefully by looking, is an arithmetic infinite. Hopefully you're seeing why that is. Infinite because of the infinity symbol as the upper index, and arithmetic because we have a linear equation. So let's think about the graph here for a moment. If I graph y equals 2x plus 3, I'm getting that line, right? So as the x values are increasing, what's happening to my y values? They just keep getting bigger and bigger and bigger and bigger and bigger. And so once again, we want the sum of this series. So I'm taking this y value and I'm adding it to that y value and adding it to that y value, and I'm adding all those y values. So just like the geometric infinite when the absolute value of R was greater than 1 a minute ago, same thing's happening here. If my numbers are continuing to get bigger, there's no way that I can find the sum. So I just say that the series diverges and no sum exists. Okay. Now, specifically, just so you know, this next thing that I write is not something you're going to need to put in your homework or quizzes and tests or anything, but just so you know for future math classes, here our d value is bigger than 0. It's positive, right? Specifically, our d value is 2. That's the slope. So when the d value is larger than 0, then the series diverges towards, this is heading up higher and higher and higher, it's going towards infinity. Okay. On the other hand, if I just throw a negative in here, then we're looking at this graph, right? It has a negative slope. And as we're going further and further to the right, as the x values are getting bigger, the y values are getting smaller, smaller and smaller and smaller and smaller and smaller. So they're getting more and more and more negative as it goes further over as the x values are getting bigger. So once again, I still can't figure out a sum. It's not leveling off. It's just getting smaller and smaller and smaller. So once again, the series is diverging, but this time it's headed towards negative infinity. So if d is less than 0, and you don't have to worry about absolute value with arithmetic, just d, then the series diverges. And again, you would still say no sum exists. But what I'm telling you is the series diverges because it's headed towards negative infinity. So it diverges towards negative infinity. Okay. Now again, this part that I have here on the right, the graphs and the explanation, that you don't need to know or repeat. I'm just telling you this because you'll, in the next couple of years in pre-calculus and calculus, you'll deal a lot with divergent and convergent. So these are terms that you're going to need to know. And you're going to want to know what they're headed towards, infinity or negative infinity. For this year, you don't need to know that. What you need to recognize is, this is arithmetic, it's infinite, and when it's arithmetic and infinite, the series diverges and no sum exists. So really, this is all I need to see. Okay. Next one. So now we've looked at some that were arithmetic and we've looked at some that were geometric, both infinite. Now you know what to do in either case. So what you first have to do is decide, is this arithmetic or geometric? So copy this one, take a look. Hopefully you can tell that this is a geometric infinite. So when it's geometric and infinite, remember we have to check the r value, specifically the absolute value of the r value. So let's look at that. The r value, you should be able to tell by looking, is 1/3. Remember, it's the base of the exponential. If you can't tell, you can always find it, though, by substituting in 1, or whatever the lower index is, and getting the first term. So if I do that, 1 minus 1 is 0, 1/3 to the 0 power is 1, 1 times 2 is 2. So I have 2. And then putting 2 in, 2 minus 1 is 1. 1/3 to the 1 is 1/3. 1/3 times 2 is 2/3. So 2, then 2/3, I can see that times 1/3, so r is 1/3, if you need to confirm that. So anyway, I'm checking the absolute value of 1/3, which is 1/3, and I am comparing that to 1. So 1/3 is smaller than 1. So when 1/3 is, when the r value is, absolute value of the r value is smaller than 1, we say that the series converges to a sum of, and now we're going to find it. So S is equal to, remember it's a sub 1 in the numerator over 1 minus r in the denominator. Let's do the denominator a while. So 1 minus 1/3, which we know is 2/3. Now in the numerator, remember, be careful. You can't always just look at the equation in summation notation and look at that first term and say, oh, that's my first number. That's my first term of this series. Remember, sometimes it is, but other times it won't be, depending on the lower index and the exponent. If that gets altered slightly, that's going to affect the number in the front, whether it's going to be the first term or not. So I always say just be on the safe side and check it by substituting the lower index in and getting the first term. Now we did that a second ago. We put 1 in, 1 minus 1, 0, 1/3 to the 0 is 1, 1 times 2 is 2. So we have confirmed already that 2 is the first term. But again, if we hadn't done that already, I would substitute in the lower index to figure that out. So a sub 1 is 2, goes in the numerator. And now we're ready to divide 2 by 2/3, which gives me 2 times 3/2, which I can simplify that diagonal there, which gives me 3. So this series converges to a sum of 3. All right, so that takes care of our problems for today. So you should, for homework, finish up worksheets 3 and 4. If you've been doing them as I've been assigning them, then you don't have actually that much to do. If you have not been doing them as I've been assigning them, then finish up whatever you do not have done on worksheets 3 and 4. Remember, Friday you have a test, and before that there will be a couple small quizzes. So make sure you now have all 6 formulas memorized. And actually, I guess it's 7 now. 1, 2, 3, 4, 5, 6, 7. Yep, 7 formulas memorized, and that you know how to use them in preparation for the upcoming quizzes and Friday's test.